So it's my great pleasure to welcome Gustavo. And I first worked with him when he was an intern at MSR. And he helped design the FlashProg user interface for extracting data from log files and web pages. And this is a demo that we continue to use to drive excitement around the company on the topic of program synthesis. So thanks, Gustavo, for that. So Gustavo finished his PhD from the University of Campa Granada in Brazil in 2014, and his dissertation won many awards. And since then, he has been assistant professor at the same university, and he has continued to be our academic collaborator, very recently running a hackathon around our Prose framework. So over to you, Gustavo, now.
Well, thank you. Thank you, Sumit, for the nice introduction. So today I'm going to talk about automating and testing program transformations using program synthesis. So developers are editing the code all the time. They need to add new features, fix bugs, or apply refactorings. And many of these code edits have already been performed in the past by the same developer. For instance, in this case, the same developer was changing an equals expression to this new invocation to the isKind method, using the right-hand side as an argument to the method. So the developer applied this to 26 locations in the Roslyn project and submitted a commit to the repository. So manually applying these edits is very time-consuming and error-prone. In fact, later we saw that there were more than 700 locations to apply this edit through the code. Another scenario is when different developers are applying similar edits to different code bases. For instance, here we have more than 100 students at UC Berkeley applying the same bug fixes to different programs. For instance, we have iterative solution and a recursive one, but both of them had the same fix that is using the term function, adding the term function call. Also in the education scenario, it's very time-consuming for teachers to provide feedback to the same bug over and over again for different students. It's nice that now there are many transformation tools that help developers and teachers and students in this domain. For instance, we have IDEs and static analysis tools that help automating repetitive edits as Visual Studio, ReSharper, and Eclipse. And we also have some some autograder tools like autograder from PLDI 2013 that automatically find a fix in the student code, and then you can generate a feedback to the student based on this fix. One of the problems with these tools is that they rely on a predefined class of transformations. So the developers need to identify which transformation they want to implement, and they need to implement this. And this is it's hard to do and hard to extend because of that. You need special skills to implement these transformations. So another problem with these tools that I'm also going to talk about is sometimes they perform incorrect edits. So for instance, a refactoring tool should apply an edit that will preserve the behavior of the code. And here we have an example of illustration of a Java program where we have a class B extending a class A. And the test method here returns 10 instead of returns 10. It calls M. That calls K from the superclass returning 10. And when we apply the pull-up method refactoring from Eclipse to move M to the superclass, now the behavior of the program was changed. The test method returns now 20 instead of 10. It calls M, but M now uses the this access, which is evaluated at runtime, and we refer to an object from B, which we'll call K from B. So it's an incorrect transformation. And this was not only Eclipse, also the just-add refactoring tool, which use formal methods to implement refactorings, perform the same change. So in this talk, I'm going to talk about how we can use program synthesis to help developers in these two activities, automating and testing program transformations. So first, I'm going to talk about a work where we propose a technique to learn program transformations from examples, and that we called Refazer, and also some systems that we build on top of Refazer. And then I will talk about a technique for testing refactoring tools. So let's first focus on this first problem of learning program transformations from example. So we saw that we may have similar edits applied by different developers. However, these edits, they have the same structure, they share the same structure, but they are not exactly the same. For instance, we can represent an edit as a tree transformation, a tree edit on the AST of the program. And here we have an edit that updates a node in the AST from K to term K, and there it's the same structure, but use different variables. So what we want is to use these examples to learn abstract classes of transformations that we can reuse in different code base. And to do so, we propose Refazer. So we give as an example, we give examples of edits that we want to learn, and then we learn transformations that satisfy these examples. So Refazer is built on top of the Prose framework, the inductive programming framework developed at Microsoft. And basically, we need to implement 3 components in this framework. We have to design a domain-specific language that represents the transformations that we want to learn. And Prose has a general meta divide and conquer algorithm to do the synthesis. This algorithm is general in the sense that it can be used in different domains. It was mainly used in the past in data wrangling, for automating data wrangling tasks. Here we will use it for automating program transformations. But also we need to implement backpropagation functions to constrain the space of search. So these backpropagation functions, they backpropagate the specification from the entire problem that you need to solve to all the subproblems that Prose create, constrain the space of each one of the subproblems. And finally, we may learn a set of transformations that satisfy the specification, but since this specification may be incomplete, these transformations may work on these examples, but not represent the intent of the user. So the idea is that we need to implement ranking functions so that we rank these transformations in order to pick the transformations that have higher probability to work on a new input. So this is an overview. Let me now focus on each one of the components that we propose. So first, let me describe the domain-specific language that we have. So our idea, as I said, is to abstract 3 transformations over the AST of the program. So for instance, we have an update edit that we want to learn expressions that represent locations where we want to match, and also expressions that represent the new AST that we want to build on this location that we want to create. So our language has a pattern matching expressions where you can match the nodes in the AST against some pattern. For instance, this pattern can be composed by concrete nodes or abstract nodes. For instance, in this case, we can have abstract node name that you can match this over all the names in the AST. But if we look at this, we can match, although this will work for this example, it will also match many other locations in the code. So we want to be more specific than that. So our language also has operators that identify a context for applying the transformation, for selecting this node that we want to select. So this context also has a pattern matching, and now we have a path within this context to the node that we want to select. So we will select a node of kind name, but within this context that is a binary expression of value multiply, and with an expression on the left-hand side and a name on the right-hand side. So we match the context, and then we search for a path in this context. So now that we know how we will select the nodes in our AST, let's see how we can update it. So one of the operators that we have in our language is the const node that allows you to basically create a new tree from the scratch. Like we just give concrete values for the tree, and we will build this tree. And this tree doesn't depend on the depends on the input AST. So this is good to use to create construct nodes that are not presented in the input AST, but we need something else, right? We need to also reuse some of the nodes of the input AST into this new node. And to do so, we also have reference operator that allows us to make reference to some of the nodes that we have in the AST. So by combining these two types of operators in our language, we can create a new AST that has new nodes, but also reuse some of the nodes in the existing GSL, in the existing AST. So this is the entire GSL that we propose. So a transformation is a list of rules, and each one of these rules represents one of the edits that we just saw. So each one of the rules represents an edit, and an edit is a map operation that maps locations to operations. And a location is a filter which will filter from all the nodes in the AST the nodes that match this pattern that is composed by context and path. The operations can be insert, delete, the normal tree operations, and then also it builds ASTs based on const nodes and reference nodes. So this is a high-level overview of our GSL. So now that I gave an overview of how we represent the transformations, the program transformations that we want to learn, now let me explain how we do the synthesis. So we have the problem of learning a set of transformations that satisfy the example. And what Prose does is to decompose this into subproblems. So in fact, a transformation is a transformation operator that has a list of rules. So Prose decomposes this problem of learning an expression of this operator into subproblems of learning each one of the parameters. And here, for instance, we have a list of rules to learn. And as we can see this, we need to constrain this space because we not even know here how many rules we need to generate. And to do so, we can implement backpropagation functions where we are backpropagate the specification to the operator to specifications to the parameter of the operator. So here, for instance, we use 3-edit distance combined with clustering algorithms to create a backpropagation function that generate this specification for this example. This specification basically says, well, we will have the rules should evaluated to a list of only one size 1, and the element in this list, the element in this list should evaluate to an edit, to this specific edit. So it should evaluate to this edit. Now we constrained our space, so we know that we don't need to have any rules, just one rule. So we try to synthesize this problem. So now we have just one problem to do. And then we keep decomposing this problem into smaller subproblems. So a rule is a map, so we need to learn locations and operations. We can keep decomposing and backpropagating the specification to the parameters of the operator. And then we can keep doing this recursively. For instance, now location has a context operator that we need to learn. And in this part, we need to use a different type of backpropagation function, because as we saw, sometimes we may want to learn the context not for the node that we are selecting right now, but we want a context, more specific context. So we want to get some ancestor of the node before selecting the node that we want. So in this case, we generate, we use disjunctive backpropagation functions to generate two specifications to the pattern parameter. So the first one is the specification of the parent, and the second one is the specification of the node itself. And then we can get the union of these problems that we solve and get all the patterns that we want to generate. Another problem here is that while in the first operator, we have two independent problems to solve. We can solve operations and then solve locations and combine both problems. Here, the problems are dependent. So to generate a path, we depend on the tree that is the context for that path. So we need, again, in this case, we need to generate conditional backpropagation functions that the specification depends on the sibling parameter. And then we keep doing this process of decomposing the problem in small subproblems until we get to the leaves and generate all the programs in that space. So for instance, here we generated all these patterns that evaluates to the node k in the program that we want. So we have very specific patterns like this one that must match first multiply expression, and then multiply expression must have a total and a k, and then we match k. Or we have very general patterns as well, match any name in the code. So the challenge is that usually we don't want the most specific one or the most general one. We want to select something in between this. And this is the last challenge that we specify, is the ranking functions. So we specify ranking functions in our technique that favor reference nodes over const nodes. For instance, if we are creating a new tree, if this tree use nodes from the input tree, this is better than just creating the tree from scratch. We favor patterns with known root paths. So we want to be not too general. So if the pattern if the path starts in the root, this may be too general. So we want to learn some context to select the node in the locations. But we also don't want to generate very specific patterns. So usually, among the patterns with no empty context, we favor the shortest ones. It's a little bit conflicting, but we try to generate not something too general or too specific. Well, so this is an overview of the technique that we propose, and we evaluated it on 3 research questions. The first one is, can Refazer learn transformations to automate repetitive edits to large C# projects? The second one is in the context of the education domain, and we want to see whether the transformations learned by Refazer can fix incorrect code of other students in the same assignment or also in different assignments.
So on the previous slide, can you say a little bit more about how did you come up with these different features?
So this was very heuristic, just trying, but we didn't do any formal evaluation of this. So this we still have a lot of work to do here. What we are trying to do now is to implement an approach like the one that Rishab did in his CAF paper, that he used learn to rank algorithm to generate weights for the features. So we implemented this in the Prose framework, but very hand-coded and without much, just with our intuition, but without much analysis of the results.
So what was the exact logic that you wrote about these features? Was it a linear combinations of these features, or was it a decision tree? Or?
It was a linear combination of the features. Yeah, we just we basically used the normal features of Prose to assign a weight to each one of the operators. Okay. So, with respect to the first research question, we selected 56 scenarios of repetitive edits applied to C# projects. So we got, for instance, 27 scenarios in Roslyn. We also got scenarios in NuGet and Entity Framework. We checked whether we could use these as examples to learn to automate these edits. So as a result, in 71% of the scenarios, the transformations that we used synthesized the same edits applied by the developers. While in 13 scenarios, it correctly applied edits missed by developers. So we reported these edits, and developers confirmed that they were needed. For instance, the first one that I shown, it was applied to more than 700 locations, and we submitted a pull request, and the pull request was accepted. But in 16% of the scenarios, it incorrectly applied more edits than it should be. And in some cases...
Could you use those as negative examples then and learn from it?
So yeah, we didn't, not yet. We didn't use it then as negative examples, but we plan to do this in the future. But we also may need to improve the expressivity of our domain-specific language, because for some of these examples, you may need type information to add, to import namespaces that are missing, or you don't want to apply this edit to every equals expression, but only the ones that have a particular type, there are object of particular type in that expression.
So, something else that occurred to me, in your context, it looked like, just from the examples you gave, it might have been a little bit too specific in the sense that it didn't take into account properties of the operators in the context. Like, for instance, multiplication is commutative for most types, and so you could, in theory, have a context that would match if it was either on the right or the left side.
Yeah, that's true. That's true. Yeah, I agree with that. We thought a little bit about adding these properties to the language. It's a nice idea. We didn't investigate it too much. So to begin with, in the start, we just need two different transformations to learn. But yeah, it's an interesting idea that we discussed.
So what were I didn't quite catch how you got the examples to generate the transformations in the first place.
In the scenario of refactorings and repetitive edits, we have 26 locations to apply the edits. We just get the examples, the first ones that the developer applied.
Just the very first one?
In this case, we got up to 3 examples.
Okay, up to 3.
Up to 3 examples, yeah. In the scenario of the students, we get the last pair of submissions of the student, the last incorrect version and the correct one, because the students submit multiple solutions to the homework. So we also evaluated Refazer on this education scenario, and we used data from the introductory programming class in Berkeley. It has more than 1,000 students per semester. And they log every information of the homework assignment. So we evaluated in 4 problems and more than 20,000 incorrect submissions, whether we could learn transformations to fix other students' code. So as a result, we were able to, using a leaving one out cross-validation, we were able to fix submissions for 87% of the students. For given this incorrect submission, we train on the rest of the examples and see if we can learn some transformation that fix this submission. And it took, on average, 5.2 submissions to find a fix for a student, while the students took, on average, 8.1 submissions to finish the homework assignment.
So was it like one rule or multiple rules you were also generating?
We are generating multiple rules. So we try to combine all the examples until we generate something that we cannot generate something that is satisfied by a transformation that satisfy all the examples. And then
try out all subsets of the rules?
We don't try all subsets. We didn't try all subsets. We just we did a square approach that we started with this, and we will this element, and we will start increasing the size of the set. And if we pick one example that doesn't fit, we just remove it and keep going until get the largest set for that transformation. But then we don't use this anymore, these examples anymore. We start from the first one that we couldn't put on the set, again adding to another set. So we don't try all the subsets. And here we just did this in a incremental way. We simulated the scenario where we don't have submissions from the previous semester. So we just need to learn incrementally. From the first time that we receive a pair of incorrect and correct submission, we learned something. And even so, we were able to generate fixes for almost half of the students.
So the things that you could not fix, were they very unique, or?
There are things that are very unique, like very far from the solution. But also, since because we are just, the examples that we use is just from the last pair of iteration of the students, we've been missing larger transformations. So in the future, we want to investigate whether we can learn from different pairs of submissions. But yeah. So this is another analysis of in the most difficult homeworks. We got the 50 students with most attempts. So there were students that took more than 60 submissions to make the homework. And sometimes we can find fixes very soon in the process. So we can we may help the student much earlier. So in this case, for instance, in the submission 24, we would be able to generate a fix, which could avoid other 40 submissions of the student. So we also investigated whether we could use these transformations learned in one assignment to other assignments. And in this case, the transformations were not so useful. They are more problem specific, but still we can use some of them into different homeworks. But this show that we may need to learn for each one of the assignments different rules. We cannot think about a general set of rules that we can encode and apply. So this was the evaluation that we have done with existing data. And now I'm going to briefly mention 3 systems that we built on top of Refazer since August.
So what do you think are the limitations of this tool today?
I think for right now, for large transformations, it may be hard to generalize. Because we learn, one student may have 5 bugs or 6 bugs. And right now, we are learning a transformation that represents the fix of all of these bugs. So it may be hard to apply the same set of fixes to other students. So it may be interesting to see how we can decompose these small transformations that the students are applying or developer.
How about the domain of, let's say, code refactoring, right? So let's not talk about the education thing. The first application that you talked about.
Yeah, in the code refactoring domain, right now the transformations are the granularity is not so big that we evaluated because each one of the rules that we learn is an edit operation, and this is kind of one rule is independent of the other. So the same thing, we need to see how we can make a combination of rules so that we make them dependent one of each other, so that we can learn a sequence of steps that the developer applied to apply that transformation. Sometimes we can learn something in this approach, like we learned larger transformations even in the student domain where we suggested a completely different solution to the student. But this, I think it's not the right way to model these large transformations, and the chances of having not the best representation of the transformation is big.
So you think maybe a different DSL might be required for that?
Yeah, I think maybe also expanding this DSL in some way as well, because right now we have these rules that are independent. So we need to see how we can maybe for each context that we learn. Right now, for each context we learn one rule that we apply. And maybe for one context we need to learn a set of rules, for instance. And in that place we will apply all these changes together.
How do you ensure that the rules that you learn are minimal? Because from just one example, if it's on the same assignment, you could learn the rule, remove everything that the student has written, and put in a constant expression that is the correct program, and that would generalize perfectly to all of the students.
I saw this sometimes. I saw this one or other time. I think the best way to deal with this is with the ranking system. We should not favor transformations that basically output the entire program without looking to the input, because we are just generating a constant and putting there as the right solution. So usually we learn all the possible transformations that are satisfy our examples, and we try to rank them so that we have the ones with higher probability to be correct.
But in a sense, according to the results that you show and the metric that you report, this would be the perfect rule to learn, because it would, with one try, it would already fix everything for all the students. So according to the metrics that you report, how many submission you correct and so on, this would be better than all the other rules that you could learn.
Yeah, but we don't use this metric for learning, for instance. Okay. It's the metric that we use it in our evaluation to report how efficient the learning was, but we don't base our learning in this metric.
But I think that the question that you're asking, and if I have to phrase this slightly differently, it's not about how you solve this problem, right? Because you have definitely clever techniques to solve this problem, but you need to have a proper baseline for evaluation.
Yeah.
Because if you did not solve it well, if you just used his idea,
and it would fix everything.
And you will still get a high success rate there.
So I think a better evaluation of especially the ranking system and the transformations that are being learned, we need to do this.
So in the data did you show how many times it gave the wrong solution? I think, I wasn't quite sure, right, in these numbers, what's the false positive rate, I guess?
So it took like, on average, 5 incorrect submissions for each student until we find the correct one. So
correct. That's okay, but what if you? So if you didn't have 5, it meant your recommendations or your transformations didn't solve the problem. Is that right? Is that the way to think about it?
I think you're mentioning how do I know whether these results are good or not? Like whether I should have learned the transformation that would fix this or not.
Well, in the case where you know the actual outcome in like a setting like this, you know exactly what the program's supposed to compute. So you can check to see if the transformation is right or not because of that, right? You have this oracle. But
exactly.
Normally you don't, right?
Yeah, normally you don't have that.
But I guess what you're saying is that every time you try and it doesn't produce the right answer, you reject that one.
Yeah, exactly.
Okay, so I would consider that like a false positive, right? If you didn't have an oracle, you would know to reject it.
Yeah, exactly. This bug fixing approach was heavily dependent on the oracle because we are basically trying all the transformations that we learned in a sequence,
right?
And see if any one of them will lead to the correct solution. But yeah.
You're not just trying all that, right? You're also trying some supersets of those, some combinations of those transformations.
No, we didn't try combinations of the transformations. This is also something that we thought about, and we saw some related work that's starting to do combinations of these.
So then a little bit lost. So earlier I thought that you were trying, so you learned these different transformations and you tried some subsets of those. No, you tried a single transformation.
Yeah, single transformation. So yeah. We get the list of transformations and try each one of them. So we don't generate subsets of transformations.
But one transformation
may have more.
Terminology is multiple rewrite rules, right?
Yeah, exactly. Yeah. So one transformation that the student did may fix 2-3 bugs, and then we may apply these 3 fixes on just one transformation. Yeah. And also for transformations that, for some types of refactorings, our DSL still cannot learn. For instance, for learning a rename refactoring, where you need to apply one local change in some point, and then apply a repetitive edit in another point. So it's a composite transformation that you need to learn. We cannot specify this as well. And in some scenarios, we saw developers doing this repetitively. So yeah, after finishing the work, we started to build some tools on top of that, especially in the education domain, because we don't want to just give the answer to the student. They say, hey, change this to that. So we built some tools that try to have a high-level feedback to the students. So the first one is mistake browser, that basically allowed the teaching staff to browse all the mistakes that were made by the students, clustered by the transformation that we learned. So in this way, the teacher can look at all the student solutions that have that mistake, and then write a feedback that he thinks is general enough to all the students, and a high-level overview of the problem, so that the students can figure out what's wrong. We evaluated this with TAs in Berkeley, and we found out that most of the clusters were conceptually consistent. Are conceptually consistent. That means that the faults that are in the cluster are the same fault. The teacher can write a single feedback to all of them. The other tool that we developed was a tool for a scenario where you don't have examples. So, for instance, in an exam, the students submit the code only once. And then you don't have these pairs of correct and incorrect to learn from. So in this case, I just play here. Yeah, so the teacher can fix the code himself, run the tests are passing, they can write the feedback, and when they submit the code, the correct feedback, we use this as an example, a pair of example, and then the teacher can look at other submissions that were fixed using this transformation. And then they can reuse the transformation, apply the fix to this other submission. It's fixed, and it can generate the same, send the same feedback to this other student. So we evaluated this tool to see whether we could, in a short time, like half an hour, whether the teachers could write fixed codes and propagate the feedback to other students. In this case, in half an hour, they had a median of 10 corrections that were propagated to more than 200 corrections. So we show that with just few examples of fixes, we can generate feedback to many of the students. Finally, another tool that we built called Trace Diff helps students to debug their code. Because in the beginning, they use Python tutor to debug, but it's very hard for a beginner to understand how to debug the code. There is a lot of information, a lot of calls and pointers. And so what we do is, since we know how to fix the code, we generate a fix. We fix the code and run both codes and compare the traces of both versions of the program. And then we can show to the student where the traces are different and how they are different, so that the student can understand which part of during the debugging process they need to look at. So for instance, the accumulate, or the values that are returned by the accumulate function, and what are the expected values at each one of the recursive calls. And the student can also go from the concrete value to more abstract values of these returns, so that they can understand what's wrong in their logic. And then they can fix the code by themselves. So we are still evaluating this. We did a small evaluation. Although we tried in 4 problems, although we didn't find a statistically significant difference considering all the problems, for one of the problems, only students using Diff trace, 5 out of 9 were able to find this the bug there, and the students using just Python tutor were not able to find the fix. Okay, questions so far? Right. So I just talked about how we use program synthesis to learn program transformations from examples and some tools that we build on top of that. Now I'm going to show how we can also use program synthesis to test refactoring engines.
So, how much belief do you have in this technology? Like, would you use this technology for implementing a language translator, or is this something that should be written by writing rules by hand?
Well, the technology, I believe we can do this, not with the GSL that we implemented so far to do this translation by example. But especially with, I don't know, maybe a good number of examples, we can find patterns that we can generalize the examples to these patterns and do that.
Well, the scenario that I'm talking about is, it's not about doing the tail end of these transformations, right? These are rules that can, so one alternative is that these rules can be written by someone once and for all, but they are tedious to write.
Yeah.
And the other alternative is that they give examples of these transformations.
Yes.
Yeah. So in the first case, they might still probably need to give examples because they want to test whether the rules are right or not.
Yeah.
Right? But for a task as sophisticated as this, would by example technologies be a good alternative, or should one resort to the manual way of writing down rules?
I think it's a good alternative, and if you look at some companies, at least, for instance, Google has already one example-based approach to apply transformations. but it's not so. It's not pure example. You need to manually specify some operations within this example. So it's not purely example.
So what is this other approach?
They call Refazer, I think, and they allow you to specify templates of edits that you want to apply over your code base. But the edits are not like concrete examples. They have parts of the examples that are concrete, but they can abstract and specify some pattern within that example. So they are using this in production code. And it's working. And I think for using a complete example-based approach to avoid the developer having to also implement this template is also possible. I think right now, for instance, our language is missing some important aspects, for instance, types, that we are not using type information. That is usually useful when you're doing these translations.
Suppose that in production codes, you used some of the examples of the edits over the code base to learn transformation, and to the extent that you know to the number of unit tests that there are there in code base, it is correct. But there are 100 of different changes all over the code base that it is applying. How would you help the developer to make a decision whether it's actually reasonable or not?
Yeah, I think it's a nice area to investigate. For instance, how we can describe in a better way what was learned, so that the developer can learn, can read the transformation and see if this is exactly what he wants to do. We can also do approaches as we've done in the past to run multiple programs that were learned. And for some locations that the programs apply different edits, we can show to the developer this difference so that he can make these changes. Yeah, we can also, like when we are showing the transformation that we learned, for each location that is abstract, we can provide examples of matches that were matched to that part of the transformation, so that he can better understand what's represented in that transformation.
So would you apply this technology to fixing grammatical errors? So let's say, some English essay or
I see. Yeah, I have been thinking about this, especially because I've seen.
We didn't catch you. Can you repeat? We didn't catch.
So would you apply this technology to fixing grammatical errors in, let's say, English essays?
Yes. I didn't thought much about this, but at some point I had this thought, especially because as second language speaker, I use one of these machine learning tools, plugin, Grammarly, I think, and it suggests many of these edits. And I think some of them can be learned by examples, if we have a good number of examples.
What about the other way around? So the techniques that those tools are using, do you think they can be a good fit for doing the kind of applications that you have?
Yes. For instance, especially for more for problems where we don't have an AST, that there is a syntax error and we cannot generate an AST, and we treat everything as text. There are some work that have been used in machine learning, for instance, to replace to insert a colon or a parenthesis at some points that are missing. Or I think we can also combine machine learning in the ranking part. I think it's a very interesting part to the combination. But I think all of these scenarios where we have a good structure, like a program or even the text, when we can parse the text using some natural language processing and you can have the structure of the text. You can think about a more structured program that you learn instead of just a function using machine learning.
One thing I was thinking here, I don't think it's been about the idea is you can have the suggestion of other changes you might want to make. When you make a change in one area, and then there's something you might want to make that change in other areas too.
If I can, so I'm just wondering if I understood correctly the question, but it's basically if I can apply this, if I can show to the developer what are the suggestions that I want to apply the transformation.
Right. As I'm typing, I make a change in here like this, then you check the rest of the code and you see you want to make this change over here as
exactly.
well. Right?
Yeah, this is a good, good user interface for the system. Yeah, I agree.
I know Refazer saves me a lot when I see that. I see the coloration. You're not using this variable.
Yeah.
Yes, I'm using it.
Yeah, exactly.
Oh, no, I'm not.
So yeah, there is this idea of, we've thought about this idea of learning a resharper by example. So we just try to learn all the transformations that developers are applying at Microsoft and get this list of transformations we learned. And we can start to suggest to other developers these transformations. It would be very interesting to see if we can rank them to see what are the most common used ones. There are some works that did this with like refactorings, that they know what are the classes of refactorings, so they can evaluate this. But now with some technology like this, we can do this for transformations that we don't have a catalog yet. And then we see what are the most common edits that developers are performing. Let's automate this one, or let's automate that one. Yeah, this is also very interesting. And see if we can also get the output of the developers as well to see whether this is a good transformation or a bad transformation to apply. So we can start to use these in code reviews to say, hey, this is not a good code guidelines here or in the company or something.
Where's an extension?
Yeah.
Yes, right.
Okay. Okay, as I said before, in this second part, I'm going to talk about this problem of these transformations can also change the behavior of the program when they should preserve it, like a refactoring. And this happens because, well, it's hard to implement refactoring too. Besides the implementation of the change itself, you need also to think about all the conditions that must be checked to guarantee that the behavior will be preserved. Like, is there any other name in this space that will have a conflict of names if I rename this variable? Or there may be many conditions to check, and usually it's a challenge to prove that these conditions are correct in a complex language as Java or C#. So the developers end up implementing a different set of conditions, and we may have overly weak conditions that allow applying unsafe transformations, that is, transformation that introduce completion errors or bug fix or behavior changes. And what they do in practice is they write a lot of test cases for their transformation tools. For instance, a test case consists of a program that they need to write, and then try to refactor this program and check what's the output. So in this case, they say that for this program, the refactoring tool should not apply because the transformation, because it will change the behavior of the program. And Eclipse has more than 3,000 test cases for this type of checking the output of refactoring tools, and still they have a lot of bugs. So they have an input program, the expected output. So what we proposed was a technique to automatically detect these bugs that leads to completion errors and behavior change in refactoring tools. And to do so, first we proposed a Java program generator called JDOG. So we specify as input the scope of the programs that we want to generate, like the number of classes, the number of methods, and the number of fields. And then JDOL will exhaustively generate programs in this scope. Then we apply for each one of these programs, we apply the refactoring under test. And then we have the Oracle problem. How do we know that the result is correct? And if there is a completion error, it's fine. It's very easy to check. But if there is a behavior change, it's much more complicated. So we proposed a tool that called Safe Refactor that generates tests for comparing the behavior of these two versions of the program. And then if the behavior is different according to Safe Refactor, we detect a failure in the test in the refactoring tool. And finally, we classify these failures into distinct bugs and report to the developers. So I'm briefly mention each one of these steps. For generating programs, JDOL is based on Alloy, a formal specification language. So you can specify, basically you can specify the scope of the programs that you want to generate and some constraints. For instance, if I'm testing the pull-up field refactoring, I want that programs that have at least one subclass declared in a field. And then you specify the meta model of the Java language. We specify the subset of the meta model in Alloy, like the type, class, field, methods, and the relationship between these elements. And use the Alloy analyzer that reduce this problem to a set-solved problem to generate all instances of the meta model in the scope that we give. So each one of these instances represents a Java program that we want to synthesize. And finally, basically, we translate each one of these programs to concrete Java code and use these programs to test the refactoring tools. So this is how we automatically generate programs as test inputs for refactoring tools. And now I'm going to talk about how we automatically generate tests for testing the input and the output. So Safe Refactor, it receives the original version of the program and the edited one. And first, it identifies the common methods between these two versions of the program. It's because we are trying to get a common API so that we can test. Because the edit may have added new methods or removed other methods that would make the test invalid. So we get only the common methods, and then we use a random test generator. In our case, we are using Rando to generate tests for these methods. And then we run the tests before and after the change and compare the results. If they are different, we say that there is a behavior change here, and this is not a correct edit. So this is just an example of test that was generated. It passes here, but it fails in the output code. So at the end, we classify all these failures into distinct bugs. The compilation errors are classified using the error message of the compiler, and the behavior change, we have some characteristics of the change that we use to classify them, but I will not describe it in details here. So we evaluated this technique, checking whether we could identify bugs in real Java refactoring engines. So we tried this using Eclipse, NetBeans, and just add refactoring tool. And we generated more than 150,000 programs to test them. And we found 34 bugs in Eclipse, 24 bugs in JRT, and 51 in NetBeans. We reported all these bugs. The developers fixed some of them, Eclipse and NetBeans. JRT fixed all of them. Then they released a new version with the fixed bugs and new additional features. And we used the same approach to test it again, and we found new 11 bugs in this tool. So it shows how hard it is to implement these refactoring tools. And even when we are fixing bugs and adding new features, you may be introducing new bugs.
So I'm just trying to understand, what was the key idea in your bug generation here? You generated random test cases.
Yeah, but we need to generate inputs for the refactoring tool. So we generate programs as inputs. And then we apply, and we use these programs to apply refactorings to these programs that we generated. So we use these programs as test inputs. And then we need to generate test case, a unit test, for comparing the original program that we synthesized against the output program, the program that was transformed by the refactoring tool.
So there were two levels of this generation.
Generation, yeah. There is one, exactly. And the testing, it's nice because since it's a refactoring, we can just generate tests that evaluate the behavior of the first program. And then we just check whether this behavior is the same in the output program. Like the first program already gives us a specification of the behavior of the program. We can get this behavior using reflection. So just run this generated sequence of method calls and get the behavior that is the values that are returned.
I think that these bugs were there, like they did not test their stuff.
So as I said, there are 3,000 test cases, and it's hard to specify this refactoring tools. There are plenty of work on proving the refactoring tools for a subset of Java, which is a lot of work. And sometimes the problem is not even identifying what is the condition that's necessary. Sometimes also implementing the condition is also hard. So another problem that they may have is overly strong conditions. So since they cannot implement exactly the condition that's necessary, they implement a simplified version that will not only reject all transformations, all incorrect transformations, but also reject correct ones. And then we also proposed an approach to detect these overly strong conditions using differential testing.
Did you try this for some other for testing some other engine?
So we try it with these 3 engines, and for C, a colleague, a friend of mine, also implemented the same approach and found bugs in Eclipse for C refactorings.
So when you say different engine, did you mean a different refactoring engine or a different engine, maybe let's say a program synthesizer engine?
No, yeah, I was talking about a different problem. For example, you can use it for testing, I don't know, a PDF parser.
Yeah. So it can be used for testing compilers as well.
Yeah.
The nice thing here in refactoring is that we have this specification of behavior, that the behavior should be preserved. So it's nice for detecting these behavior changes that are hard to get. But we can also generate tests for compilers and see at least if the compiler is compiling the code without errors. And then there are some work that do like differential testing. So we can generate all these inputs and run on different compilers and see whether the compilers are returning the same result. And if it's not, you can investigate which one is correct. But it's also interesting. Here, with respect to the refactorings, we evaluated on 10 different types of refactorings.
So there's been some work on deriving optimizations or translations from proofs, like the Vellum work at UPenn. So do you think such an approach can be applied for refactorings as well?
Yeah, but sometimes it's just hard because the semantics of the language sometimes is not even formally specified. So for some operators in Java, you not even know exactly what exactly it should return. You can try to specify this formally, but also for, I've seen some works that did this for Java, but they just used copy semantics. They just didn't use reference. and still it was plenty of work to prove all these transformations. But yeah, it's just proving for the entire language will be very challenging. Okay. So yeah, I just presented these two past works that we did using program synthesis for automating and testing program transformations. I will just briefly mention some feature work that we are working on. The first one of natural ideas that I had from these two past work is how we can combine both of them. Like we reported a lot of bugs to Eclipse developers, and they said, "Oh, nice, thanks for reporting these bugs, but can you also help me fix them? Because you're reporting 100 of these bugs, it's hard to fix them. You need to implement a new precondition for each one of these bugs." And the idea is using these testing techniques for generating examples of inputs that the refactoring engine should accept and inputs that should not be accepted. And then input programs, I mean. And then we can use inductive programming synthesis for learning preconditions based on the characteristics of these inputs that are positive and the inputs that are negatives. And then we can embed these preconditions again in the refactoring engine and test them again. And we can do this in a loop so that we can see if we are not adding overly strong conditions and then refine these conditions again and again and again. So this is a work that we are starting to do. As I said, we also want to improve our GSL, adding types. For instance, looking at Google Refazer language, we are thinking how we can also support the type of transformations that they implement. So we want to say that this expression has type string, and then we will match it, and only if the type is string. And also using variables, because right now, in the template that we have, we only use one variable of the that is generated by the filter. But here we may select this entire expression in the filter operation, but we want also to use variables within this this location to reuse them, to assess them in the right-hand side of the template. So yeah, we are working on machine learning-based rank systems. As I said, mining repositories. Some universities, as Berkeley and MIT, are interested in using Refazer for their introductory programming classes. And also we got some feedback from people from data science and machine learning classes where this can be also very interesting, because in that domain, just by the test case, the correct output and the incorrect one, it's very hard to understand where is the problem, like what I made wrong in this loss function, or what I made wrong when I was doing all my data wrangling task to generate some statistics. I know that the value is incorrect, but I'm not sure why. So techniques that can generate hints about what's wrong and pinpoint the code, or the part of the code that's wrong, can be very interesting in this domain.
How would Refazer help with that?
We can learn from other students. If we learn these transformations in these different languages, for instance, you can use transformations in R or in Python to implement.
So you're assuming that other students also made.
Yeah, exactly. Yeah, so we can learn from these other students these edits and apply them. Okay. Yeah. Thanks.
Any more questions? Okay, thanks, Gustavo.
Thank you.